With the advancement in drone technology and the increase of their popularity, many are turning their hobby into a semi-professional career to make some extra cash. Some of the most popular RPAs being used are the 3DR Iris, DJI Phantom series, and the new to the market DJI Mavic. Although these are off-the-shelf drones, they are already made to have first-party modification done to them. Some, such as the 3DR Iris, have support for third-party modification. With the battery placed in a more accessible area, subsequently changing the COG and demanding different usage from the motors, it would affect the RPA's endurance. Why is this important? If you need more room on the inside of a quad rotor for some new mission critical tech, then you may have to move the battery to the outside, and is it safe to do so? Before the investigation, it is important to explain first what an RPA is, the laws governing them, safety while working with and around a quad, and the systems and math that underpin how a quad rotor flies. RPA stands for Remotely Piloted Aircraft in most parts of the world. In America, they are referred as UAS or Unmanned Aerial Systems. The RPA that was used in the investigation was a 3DR Iris, and due to the method of investigation, the RPA is classed as an RPAS, or Remotely Piloted Aerial System. This is because of the onboard autopilot that was used during the investigation classifies it as an aerial system, not just an aircraft. Just like any branch of aviation, there are laws and regulations that govern how you can and cannot use your quad rotor. Most councils and estates will have their own laws by which need to be followed within that area. However, these regulations, at minimum, need to comply with the Civil Aviation Safety Authority, also known as CASA.
CASA write the regulations and govern all branches of aviation in Australia. For RPAs, the regulations and guidelines are within a document from CASA called the Civil Aviation Safety Regulations 101, or CASA 101. Some of the most important safety guidelines in CASA 101 also come on a yellow leaflet handed out by CASA. This handout is designed to give everyone a quick understanding of some of the basic rules required to follow when flying an RPA. These rules include: only operate your aircraft in your line of sight in daylight, must not fly closer than 30 meters from a vehicle, boats, building or people, and one of the biggest regulations, you should not fly within 5.5 kilometers of an airfield. Following these basic safety rules ensure that no persons or property is at risk. How do RPAs fly? The most common RPA, and the one used in the investigation, is a quad rotor. They have 4 motors, usually in an X layout, with motors spinning at different or same speeds to control the movement. Depending on how fast, if all 4 motors are spinning at the same speed, then the quad will either gain height or lose height or hover. If the front motors spin faster, the quad will pitch back. If the back motors spin faster, the quad will pitch forward. Left and right motors control roll in the same way. Yawing utilizes the rotational torque of the diagonal motors to control the yaw axis. These axes and throttle movement are controlled via a transmitter. The transmitter is the device that communicates with the receiver in the aircraft by sending signals through the antennas. This signal is known as a pulse width modulation, or PWM. These pulses is what causes servos or motors to change their movement. The pulse is between 1 and 2 milliseconds, with 1.5 being the neutral or halfway point, and have 20 millisecond gaps between them. The pulses are interpreted by the receiver and sent to the required servo or motor.
The main query, as stated before, was by making the battery more accessible, subsequently changing the COG and demanding different usage from the motors, how would it affect the RPA's endurance? It was hypothesized that the drone would require more power, as the engines would have to compensate for the adjusted center of gravity by increasing the throttle output, thus using more battery power. You may be asking yourself, why would we do this? We decided to research and investigate this for 2 reasons. Number 1, if you needed more room on the inside of a quad rotor for some new mission critical tech, then you may have to move the battery to the outside. And reason number 2, batteries get puffy over time and won't fit in the designated battery compartments, as we found out during our testing. So it is practical to move the battery's position. To find this out, 2 sets of data were chosen to obtain from the mission after each flight: the flight times and the depletion percentage of the battery. We chose to do 9 flights, 3 flights with the battery in each position, to find the average and any other data trends. Now, all this is useless if the battery remained in one position. The first 3 flights were control flights with the battery of the Iris placed in its intended spot inside. Our second set of flights were with the battery 5 centimeters closer to the aft inside the battery compartment. This would create what's known as a tail-heavy COG, requiring more power from the rear motors. The last 3 flights were with the battery approximately 5 centimeters forward of the COG. This creates a nose-heavy COG that requires more power from the front motors. A set flight path was chosen to test all 9 flights, and to make sure no human error was involved, the 3DR Iris's onboard autopilot was used. After completing all 9 flights and measuring flight times and the battery percentage, the results were surprising. It was noted that on the 3rd flight with the battery in the normal position, the percentage drop rose by 4%. This could have been due to the quality of the battery, as the inconsistently happened twice, once after each battery position. The first flight with the COG back has a lower percentage drop, and the 3rd flight with the COG forward also has a lower percentage drop. This can be seen in the battery percentage graph. Excluding inconsistencies, the average drain on the battery is noticeably higher with the battery moved forward from its designated location. An average of 5% was drained when the battery was in its normal position, 6% when the battery was further back, and 6.3% when the battery was further forward. The voltage graph shows another way of confirming these results. The battery discharging quicker wasn't the only significant find. The average flight time increased as well. Requiring more power from the motors and having longer flight times reduced the efficiency and the endurance of the quadrotor and the battery. If it was absolutely necessary, having the battery slanted forward is better than backwards. It can be seen in the flight times versus battery depletion graph that even though the flight is slightly longer, the percentage drop is smaller. This is because of the front motors. When the COG is nose heavy, they need to spin at a speed just enough so the quadrotor keeps stable, but this also slows the airspeed. The reason why backwards is less is because even though it is a shorter flight time, it uses more power than necessary because of the aft motor spinning faster, to not only push the quad forward, but to keep the quad stable at the rear. The most significant reason to not move the battery is the instability it causes. While the quadrotor was flying with both the COG forward and backward, when the quad turned, there was a more amount of roll and wobbling. This is dangerous as a gust could easily flip the RPA and cause it to crash. Takeoff and landing were also slow, with the prop wash having a great effect when landing. This investigation has confirmed what would happen when the battery was moved. What were the effects of the COG change? There was an increase in motor usage from the front and aft motors when the COG was changed, respectively. This ultimately caused a higher discharge of the battery, resulting in reduced flight time. Not only was there less available time in the air, performance of the drone decreased significantly, with reduced stability while taking off, landing, and maneuvering. The RPA also moved at a slower velocity, further decreasing the efficiency of the quadrotor. It is highly advised that users of quadrotors read and follow the guidelines of the RPAs before flying, and avoid changes and modification to the aircraft as much as possible.